In chemistry, there's kind of this secret code. It's this one single idea that lets scientists connect the invisible world of atoms with the stuff we can actually see and hold. It's the absolute key to predicting and controlling the reactions that make our world work. So today, we're going to crack that code. We're going to finally understand the mole. Okay, so imagine you're a chef, but your ingredients are so ridiculously small you can't even see them, let alone count them. How in the world would you follow a recipe? Well, that's the exact problem chemists have to deal with every single day. So how do they pull it off? Before we get to the solution, let's just take a second to really appreciate how huge this problem is. I mean, when you get down to the atomic level, all our normal ways of measuring things just totally fall apart. Look, the mass of a single atom it's almost nothing. It's so small. If a chemist tried to do their job by weighing out one atom at a time, they would get literally nothing done. It's just not going to happen in a real lab. They needed a better system. They needed a bridge, something to connect that invisible world of tiny little atoms to the world of grams that we can actually measure on a scale. And the solution they came up with is actually pretty brilliant. It's called the mole. The easiest way to think about it is like this. It's a chemist's dozen. You know how a baker doesn't count every single egg for a giant order? They count cartons? Well, a chemist groups atoms into moles. It's just a way of counting by using a much, much bigger bucket. So what is a mole, officially? Well, it's the standard unit for the amount of substance. Just like we use kilograms for mass or meters for distance, chemists use the mole to count particles. Which, of course, leads us to the really big question. How many particles are we talking about here? And there it is, 602 sextillion. That is the number of particles in just one mole. It's a number so huge it's almost impossible to even wrap your head around. It's got a special name, the Avogadro constant, and it is the absolute heart of this whole chemical code we're trying to crack. But look, don't let that insane number scare you off. The concept itself is super simple. If you ask for a dozen donuts, you get 12. If a chemist needs a mole of carbon, they get that many atoms. A mole is just a handy name for a specific, and yes, a very, very big number. So, okay, we've got this gigantic counting number. Great, but just knowing the count is only half the job. The real magic, the genius of the mole, is how it connects that invisible count to a mass, to something we can actually weigh out in a lab. This simple little formula is the bridge I was talking about. It just says that the mass of something in grams is equal to its relative formula mass, we'll just call it m sub r, multiplied by the number of moles. That m sub r is basically just the weight of 1 mole of that substance, and you can find it right on the periodic table. It's the key that unlocks everything. And hey, here's a great little trick to help you remember that formula. Just say mass equals Mr. Mole. It's catchy, it's easy, and it is the key to so many chemical calculations. Let's actually see how it works. All right, let's try a quick example. Let's say we need to find the mass of a quarter of a mole of carbon dioxide. First things first, we just write down our formula. Mass equals m sub r times moles. Okay, step 2, we just plug in the numbers. The relative formula mass for carbon dioxide is 44. So we just pop that and our 0.25 moles right into the equation. And finally, we do the math. 44 times a quarter is, of course, 11. So a quarter mole of CO2 weighs exactly 11 grams. And just like that, using nothing more than a simple scale, we've measured out a specific astronomical number of molecules. Pretty cool, right? So this is where it gets really powerful. Now that we can switch back and forth between mass and moles for one substance, we can start to decode entire chemical reactions. So a really key idea here is something called the limiting reactant. Basically, in any reaction, you're pretty much always going to run out of one of your ingredients before the others. That one ingredient is what stops the whole process, and it decides the absolute maximum amount of product you can make. Let's go back to baking. If a recipe calls for 2 eggs and a cup of flour, but you've only got 1 egg, well, it doesn't matter if you have a mountain of flour. The egg is your limiting reactant. You can only make half a cake, period. Chemistry works the exact same way. So if we want to predict how much product we're going to get from a reaction, we need a little checklist. We need the recipe. That's the balanced chemical equation. We need to know how much of our starting ingredient we have, our limiting reactant. And finally, we need the relative masses for everything involved. Let's run through one. Say we start with 12 grams of magnesium. Step 1 is always the same. We have to convert that mass into our universal currency, the mole. So we just flip our formula around. Moles equals mass divided by relative atomic mass. 12 divided by 24, that gives us half a mole of magnesium. Easy enough. Now, step 2. This is where the balanced equation becomes our recipe. It tells us the ratio of ingredients. See how there's no number in front of the Mg or the H2? That means for every 1 mole of magnesium we use, we make 1 mole of hydrogen gas. It's a 1-to-1 ratio. So if we start with half a mole of magnesium, we have to make half a mole of hydrogen. And for the final step, we just convert our answer from the mole currency back into a mass we can measure. We use our trusty formula one more time. Mass equals m sub r times moles. The m sub r for hydrogen gas is 2. We multiply that by our half a mole, and we get exactly 1 gram. We just predicted the outcome of a chemical reaction before it even started. Okay, but what if you don't even know the recipe to begin with? This right here is where the mole concept is just amazing. We can use the exact same logic, but backwards, to figure out the chemical equation just by weighing stuff. Check out how this works. Let's say we do an experiment and find that 6 grams of magnesium reacts with exactly 4 grams of oxygen. Step 1, you guessed it, we convert those masses to moles. That gives us 0.25 moles of magnesium and 0.125 moles of oxygen. Now, here's the clever trick. To find the simplest ratio, we divide both of those mole numbers by whichever one is smaller. In this case, 0.125. And what do we get? A super clean ratio of 2-to-1. And that is our recipe. It tells us that it takes 2 magnesium atoms for every 1 oxygen molecule. And from there, we can write out the whole balanced equation. That is incredible. So as you can see, the mole is so much more than just a big number. It's the translator. It's the bridge between the world we can see and the world we can't. It's the one thing that turns chemistry from just watching stuff happen into a powerful, precise, and predictive science. The mole lets us become architects of the molecular world. We can design and build new things with incredible precision. So I'll just leave you with this thought. Now that you've gotten a glimpse of the secret code that chemists use to build everything around us, what would you create?